Hi, I'm Nicole, and this is Lab 4 Oscillations. The purpose of this lab is to analyze and model a spring mass system in which the mass moves in a two-dimensional oscillating motion. Our goal is to obtain the position and velocity of the oscillating mass, as well as to examine the relationship between kinetic, spring potential, and gravitational potential energies of the system. So again, our objectives are to analyze the spring mass system's motion in Tracker, then create a computational model in GlowScript. We want to then compare the predicted and observed motions of the system, and then lastly, we want to plot the energy changes associated with the system's motion. The physical principles in this lab consist of the momentum principle, Newton's second law, specifically the velocity update equation and the position update equation, and then also the energy principle. So when using Tracker, we were told to calibrate the oscillating mass to 0.402 kilograms and to calibrate the length to 0.7 meters. The graph to the right is the y component of the position data, showing that the mass is oscillating. However, it also explains that because the mass is oscillating, the position calculations will be both positive and negative. It's also important to note that the system includes the spring mass and the Earth. The forces involved are the spring force and the gravitational force. And then additionally, the energies that we'll be looking at will be kinetic energy, the spring potential energy, the gravitational potential energy. And again, the entire purpose of using Tracker was to collect points from the center of mass of each frame to form a position versus time graph, which is the one shown to the right, to observe the motion of the oscillating mass. Additional information was needed to make the computational model, such as determining the spring stiffness, which was calculated by manipulating the period formula. And then also we had to determine L0, or the relaxed length of the spring. We found this by setting the magnitude of F grav equal to the magnitude of the spring force, and then manipulating this equation to isolate L0. The code had three main components to it. First was inputting the initial conditions that were obtained from our Tracker file data, which included the system's mass, initial position, and initial velocity. The second one establishes the data needed for the energy principle, which is the spring stiffness and L0, as well as the formulas for the components of the energy formula, which can be expressed as the sum of the kinetic energy, gravitational potential energy, and the spring potential energy. The third component is the bulk of the code, which consists of the iterative calculation loop, which determines the position of the mass using Newton's second law. It also updates the mass's position, velocity, and calculates the energy changes. The result of the code finds the predicted motion of the mass while also documenting the energy changes of the system as it oscillates. Looking at the top graph, the orange line, which represents the total energy, is equal to 0. Looking at the second graph, the blue line is the computational data graph, while the red line is the observed motion data graph. The graph in general does show that both data sets are fairly close to each other. However, the observed data does seem to have a slightly elongated period as it extends, whereas the computational data has a very fixed or consistent period. In conclusion, this graph shows good reasoning of the energy principle. The position graphs have fairly good matches in terms of the oscillation periods. However, there was something that caused the observed model to have elongated periods, potentially due to the spring slowing down or due to my center of mass shifting. For the what does it mean segment of this lab, first, is the energy principle satisfied? I said yes, the energy principle was satisfied. This is demonstrated by the graph where the gravitational potential energy and spring potential energy have the same amplitude but are of different phases. Also, the change in energy is equal to 0 because the orange line that we observed earlier had a flat slope, and this is due to there being no work done by the surroundings. Moving on to the next, we were supposed to make two separate estimates of oscillation periods. First, by estimating the period of oscillation from the X position data, and then second, by estimating the period of oscillation by the Y position data. So for the X position data and for the Y position data, we had fairly close numbers. For X, it was 1.61 seconds. For Y, it was 1.55 seconds. Although the period for oscillation for X and Y weren't too far apart, they were calculated differently. The X period of oscillation was based on the spring moving left to right, while the Y period of oscillation was based on the spring moving up and down. But also, because the X component of the oscillation is longer, we can conclude that the object is not moving in a perfectly circular motion.